Hey everybody, welcome to another lecture video. This time we're looking at chapter 14 and we'll be talking about acids and bases. Now, let me just get set up here. Sorry. Okay, so acids and bases. Now, you probably remember our talk about acids and bases when we went into, was it chapter 7? And we were looking at chemical reactions. And chemical reactions, neutralization reactions or acid-base reactions was one of those specifically that we looked at. You also probably have some general idea about acids and bases, but we're going to talk about a few of their properties anyways. Acids are used often in movies as special effects used to dissolve, on Breaking Bad people or on, James Bond movies, like the picture here, metals, not gold bars, prison bars and that kind of stuff. Now, acids do taste sour. They do all have something in common. They all produce hydrogen ions. And this is true of HCl, which is sort of being depicted here in the James Bond picture, but also in this picture on the side here of a lemon. This is probably some kind of citric and tartaric acid. But anyways, whenever you eat something sour, let's say like a Sour Patch Kid, or you taste a lemon, there's usually, in the case of the candy, a white powdered coating that has a mixture of those acids in it, citric acid and let's say tartaric acid. Or if you eat a lemon, you'll get those directly. And these will mix with the saliva in your mouth, basically the aqueous solution, right? And they produce hydrogen ions. Sometimes you see it shown like this. These are equivalent to each other. We call these hydronium. This is a hydronium ion, or a hydrogen ion. Now, in our mouths specifically, we can actually detect this because those hydrogen ions will once they're released from the acid, they react with our protein molecules on our tongue. Protein changes shape, sends an electrical signal or a nerve impulse, however you want to describe it, to your brain, and that's essentially what you experience as a sour taste. So the sour taste is going to be a direct response to anything you eat or put in your mouth that is going to liberate hydrogen ions. So you basically have a sour detector right there in your mouth. Now, of course, if the sourness or the acidity is too much, you're just going to damage all of those proteins in your mouth because we're gonna see acids are very corrosive. Okay, so in the case of dissolving metals, such as in the James Bond movies, often there's like a gold pen filled with acid or something, and the pen being made of gold is important because it is one of the few metals that does not get dissolved by acid. So gold doesn't dissolve by most acids. Now, there is a way to dissolve acid, and it requires a mixture of a couple of different acids together. I think the term for it is aqua regia, because it's used to dissolve gold. Anyways, this is a neat way to hide your gold too, right? If you had someone looking for your gold, you dissolve it all, let's say in the sink or in a bathtub, and it just looks like water, and then later you precipitate your gold back out. But anyways, going back to the movie example, so when James Bond or someone's imprisoned, right, he squirts some of this acid out of his pen onto the iron bars, and then of course they dissolve. Now, with enough acid, it is possible to dissolve iron bars, especially iron in a prison cell. But it would take more acid than the amount that fits in a pen. And so that's where movies sort of just take liberties, where science has to say, oh, that wouldn't happen. A small piece of, let's say, aluminum, I think this is aluminum here, placed in hydrochloric acid will dissolve away in about 10 minutes, but you have to have a stoichiometric amount of acid, and we're going to see that when we start writing some acid-base equations, that we're going to have to balance them. So definitely the acid contained in a pen is not going to be enough to, melt or dissolve any significant amount of metal. As far as acid properties go, they have a few properties. They are sour in taste. Acids will dissolve many metals, so I guess we could just write dissolve metals. And acids will turn blue litmus paper red, and that's what we're looking at here. So the acid is in this area, and it's turned this litmus paper red. So we could use this litmus paper, this as an indicator for acidity. And you might, if you have a pool or a spa, if you've ever maintained the pH of something, fish tank, you probably have some kind of pH paper. All right. Let's talk about some acids. So, some examples. So, hydrochloric acid is found in most chemistry labs. It's used to clean metal, prepare and process foods, to refine metal ore. Hydrochloric acid is the main component in stomach acid as well. It helps break down your foods, it kills harmful bacteria, and so on. And the sour taste associated with indigestion, or I guess even with throwing up, is caused by the hydrochloric acid, refluxing up into the esophagus. So if you have acid reflux disease, you know what this tastes like. If you've ever thrown up and you get this in your nose and in your mouth, it doesn't feel good, but it also has a sort of a taste to it, and that's again hydrochloric acid that's inside your stomach. Sulfuric acid. So that was HCl. Here's sulfuric. One of the most widely produced chemicals in the United States. I think the annual production of sulfuric acid actually exceeds 36 million tons a year. Sulfuric acid and nitric acid are commonly used in the laboratory. So nitric acid shown here. Sulfuric acid and nitric acid are used in the manufacture of fertilizers, explosives, dyes, glue. Sulfuric acid actually is also contained in automobile batteries. So there's a lot of uses for those guys. We've got acetic acid here. I moved it up to the top. This actually forms in improperly stored wines. Vinegar, the word, actually comes from the French vinaigre, which means sour wine. So that's, again, improperly stored wine, you lead to vinegar. Acetic acid forms. Acetic acid is an example of a carboxylic acid. So this is a different sort of class. We looked at binary acids. We looked at oxyacids. But we didn't spend much time looking at carboxylic acids. So just to tell you what those are, they are acids in which there is a C bonded to a double bonded to an O, and then there's an OH attached to that, and it's that H that falls off during the chemical property of acidity, losing the H. It's that H, and again, here's another one that you can kind of see. All carboxylic acids will have this functional group. We call them functional groups. So acetic acid is one of those, and sometimes we also just call it, or note it as a COOH. And here's a couple more carboxylic acids, citric acid and malic acid. Now, we often find carboxylic acids in substances that are derived from living organisms. So, inside apples and oranges and lemons and that kind of stuff, we're going to find, even in our bodies, we have some acids. Lactic acid, for example, forms in our muscles. Okay, just to mention what citric acid and malic acid were. Citric acid, you find it in lemons and limes. Malic acid in apples, grapes, and in wine. Okay, let's talk about bases. Bases have the following properties. They are bitter. They are slippery. They turn slippery. They turn red litmus paper blue. So again, you can use red litmus paper to detect basicity, blue litmus paper to detect acidity, and the color change will indicate that. Now, all of these consumer products that I'm showing you here in this picture contain bases. They're slippery because they react with the oils on your skin to form soap-like substances. When we make soap from fats, we use bases to do it. Soap itself is basic, and its slippery feel is characteristic of bases, so that's just another sort of confirmation on this observation here. Some household cleaning solutions, such as ammonia, are also basic, and they also have a slippery feel because of the base. Okay, So I mentioned that bases taste bitter. I'm going to show you some molecules here. So bases are less common in foods than acids because of their bitter taste. Our aversion to the taste of bases is probably an adaptation to protect us from alkaloids. Alkaloids are produced by plants. They're organic bases. They're often poisonous. The active component of hemlock, for example, is the alkaloid coneine. I don't know if I'm saying that right. And their bitter taste actually warns us against eating them. So some foods contain small amounts of base, like coffee. Coffee is acidic overall, but bases present in coffee, such as caffeine, impart a bitter flavor. So caffeine is actually a base, even though the solution of coffee is acidic. And that's where the bitter flavor comes from the base here. Some poisons are actually, undetectable, and I think I mentioned to you guys that there's an adaptation that some humans have where they can actually detect one of these poisons. I forget if it was arsenic or cyanide, something like that. But again, because it's basic, it'll probably taste somewhat bitter, or most likely it's going to be an alkaloid if it's made by plants, which is going to be an organic base. So basic. Okay, let's define some. Actually, I didn't give you any examples of bases. Let me give you some examples. Some base examples: sodium hydroxide, also called lye, and potassium hydroxide. These are often found in chemistry labs. They're used in processing petroleum and cotton, in soap and plastic manufacturing. Sodium hydroxide is the active ingredient in products like Drano that unclog drains basically by just kind of dissolving them. Sodium bicarbonate, NaHCO3, is baking soda, active ingredient in many antacids. When you take an antacid, the sodium bicarbonate neutralizes the stomach acid. This relieves heartburn and a sour stomach. Okay, so now let's talk about the definition. So an acid, at least by what we're going to call the Arrhenius definition, an acid produces hydrogen ions, so H ions, in aqueous solution, meaning in water. So HCl is a covalent compound, right? It's made out of only nonmetals, so it's molecular. There's no ions. This would be called hydrogen monochloride. But when we put it in water, I got an equation for you here. When we put HCl in water, we can show it actually ionizing into the hydrogen ion and the chloride ion. Now, hydrogen ions are highly reactive. In aqueous solution, they bond to water molecules according to this reaction. So I'm going to write it out for you. H plus will react with a water molecule to form something called H3O plus. Now I mentioned this before. Let me draw it for you in the Lewis structure. So this is hydronium, H3O plus, or hydronium ion. In water, hydrogen ions always associate with water molecules. So as long as there's water present, this is the reaction that's happening. Now, often chemists will just use H plus instead of H3O plus because it's a lot easier to balance an equation. For example, to write this equation that shows that HCl reacts to form or ionizes to form H plus and Cl minus, we don't have to show any water molecules. But to show an actual balanced equation with H3O plus written here, you can see right off the bat we're missing a couple O's on the other side of the equation. So we'd have to include the water molecule in this whole setup. So just being able to not have to write a water molecule makes everything easier. So just, in case you see H3O plus in the reading or see it somewhere, try to associate that with basically what we're saying is just the hydrogen ion. That's the acidic part of the water. I'm going to show you a few more right now. So we write the formula for acids as having the H in front. So for formic acid, for example, the formula is HCHO2 and not CH2O2, right? The H in front means it's an acid.
In the Lewis structure, we would actually see that that H is attached to an O, and in that sense, it's actually, you can see here, if you remember from a few minutes ago, this is a carboxylic acid. This C double bond O with an OH on it is a really good group for letting hydrogens go. And we won't get into why that's true because that's beyond the scope of this class, but let's just say there are some molecules that are really happy to have negative charges on them. For example, a Cl minus is a really happy ion because you guys remember it gained an electron. It looks just like the noble gas that's right after it. And so this is comfortable like this. We don't see in this reaction down here a lot of chlorines trying to get their hydrogen back so that it can become HCl again, right? In fact, we call HCl a strong ion, a strong electrolyte, because it completely breaks apart, and it has little interest in going back the other way. We'll see in a moment that there are weak acids that don't exactly do that. And then for this carboxylic acid over here on the side, when this hydrogen's gone, we end up with some lone pairs here and a negative charge. And again, this negative charge is resonance stabilized, meaning that sometimes the double bond shifts down here and lets the negative come up to that other O. And since this can go back and forth, that's what stabilizes this molecule. All right, as far as how we would write the ionization of this, we would say HCHO2, and water will be H plus and CHO2 minus. So that's sort of mirroring what we're seeing down here. So the acid and then hydronium and the leftover of that acid. We're going to give it a name in a minute. We haven't named what that substance is. But again, to spot an arenous acid, we want to see that it forms hydrogen ion in the product. Okay, the arenous definition of a base produces hydroxide ions. Remember, hydroxide is OH minus. Sodium hydroxide is an arenous base because it produces sodium hydroxide in solution. Let me show you. Right down here. So we've got NaOH. When it ionizes, it produces Na plus and OH minus. So that OH minus being present there is what makes this an arenous base, because arenous bases directly make hydroxides. This is a definition. We're going to get to a better definition of a base in a minute. This is how it started, though. This is when early scientists were trying to figure out what's an acid and what's a base, and so this definition made a lot of sense. Something that added hydroxide was a base. Something that added hydronium was an acid, added to water, that is. So molecular compounds containing a OH group, such as methanol, don't necessarily act as bases, and that's because they don't dissociate. So let me show you what I mean. We have something like KOH. It's ionic. This breaks into K plus and OH minus, right? That's a base. We've got NaOH. We already looked at it. Let me show you a different one. How about aluminum hydroxide? Right? If this thing ionized completely, right, we would have a bunch of hydroxides being released. So those are all bases. Now, on the other hand, we have CH3OH. Okay, this thing has OH in it. Let me show you what it looks like. So this is methanol, CH3OH. Now, this OH right here doesn't come off, right? The OH doesn't fall off of this molecule. This is covalently bonded, right? Lewis structures, shared electrons, all that stuff. So not everything that has an OH in it is a base. Has to produce OH ions in solution. Now, when we take acids and bases together, the Arenas definition basically says that acids and bases will naturally combine to form water, and they neutralize each other in the process. So an acid in solution produces hydronium. a base in solution produces hydroxide, and allowed to react, they will produce water and cancel each other out. So that's what happens under the Arrhenius definition. So now there's a better definition. We're going to talk about the better definition here. So the Arrhenius definition doesn't always explain why some substances act as bases, even though they don't contain hydroxide. And so the Arrhenius definition does not apply to non-aqueous solvents. Basically, it doesn't apply to things that aren't water, for example, or that aren't. Well, first off, the Arrhenius definition only applies to water solutions and not any other type of solution. And we'll be able to learn, and if you ever go to organic chemistry, you'll learn that there are solutions that don't have water in them that can be acidic or basic. The Bronsted-Lowry definition of acids and bases actually applies to a wider range of acid-base phenomena. And this definition focuses more on what we'll call the transfer of a hydrogen or a proton, transfer of a hydrogen ion. And since a hydrogen ion is a proton, a hydrogen atom, right, without its electron, and remember hydrogen just has one electron, one proton, so if you take away its one electron, that's what gives it its positive charge. All that's left over is its one proton, so it's just a proton. So we often call something a proton acceptor or a proton donor. Proton donors or acceptors. So in the Bronsted-Lowry definition, an acid is going to be a proton donor, and a base is going to be a proton acceptor. Now, in 1923, Johannes Bronsted, working in Denmark, and there was a different guy, Thomas Lowry, working in England, developed the concept of the proton transfer, and so we named it the Bronsted-Lowry definition. So according to this definition, HCl is a Bronsted-Lowry acid because in solution, it donates a proton to water. So here, we're not just looking at HCl and saying, oh, it formed H plus and that's why it's an acid. We're saying it had a hydrogen on it, the molecule HCl, and then at the end it doesn't have a hydrogen on it. Where'd that hydrogen go? Well, there was a water molecule that now has an extra hydrogen. So HCl was a donor of a proton. Anything that'll donate a proton will become an acid then, according to this definition. And it works. It helps to explain basically what happens to the hydrogen ion, when it dissociates from that acid. The Bronsted-Lowry definition works well with bases such as ammonia, NH3. They don't have any OHs in them, so we wouldn't call this guy a base because when you look at it, it doesn't have a hydroxide, and so you wouldn't think it can produce a hydroxide. But instead, it still produces hydroxide ions in solution. It's a base because it accepts a proton from water. So if you look at NH3 and H2O, and then what happens after they're allowed to react together, we get NH4 and OH. So this guy right here lost a hydrogen, minus an H plus. And from here to here, it gained an H plus. So they just swapped a hydrogen. There's still only 5 hydrogens altogether over here, and there's still only 5 hydrogens over here too. So proton transfer, proton donating, and proton accepting. So this was the acid, this was the base. Now, forward and backwards directions can also happen. And so let's take a look at that. So in the Bronsted-Lowry definition, these acid and base reactions always occur together. So in the reaction between HCl and water, HCl is the proton donor, and water is the proton acceptor. And in the other reaction, the one between, let's see, do I have them both? And the one between ammonia and water, the water was the proton donor, and ammonia was the proton acceptor. And I'll just want to take a moment real quick and just point that out. that water was a base in one reaction and it was an acid in the other. So sometimes water acts as an acid, sometimes water acts as a base. And we're going to form something called conjugates. And so I want to show you that here in a second. I'm sorry, the water thing. There's a term for this when something is an acid or a base. We call it amphoteric. And this just means that a substance can act as a proton acceptor or a proton donator, depending on what it's paired with. So let's take a look at the reverse reaction. So in the reverse reaction of this one right here, so we looked at it going this way. We saw that the ammonia was the acceptor, water was the donor, and that we formed ammonium and hydroxide, okay? But if we were to look backwards now, so going this way, we can see that their roles are going to switch. So this hydroxide, which was the the leftover of the acid, the water was the acid, right? The acid. It was the proton donor. It lost its hydrogen, and now it's hydroxide. It's going to be an acceptor in the backwards direction. This hydroxide is going to gain a hydrogen in order to become water again. So that makes whatever's left over from our acid, we're going to call that the conjugate base. And that's why they're both in red here and connected with this line. This is showing us that they're a pair, they're a set. Let's look at the other one. So we had this guy as a base, ammonia. It gained a hydrogen, because that's what bases do. It became ammonium. Now in the backwards reaction, if ammonium is allowed to react with hydroxide and form new products going this way, we see that it is going to be the acid, because ammonia has an extra hydrogen that it can give away to hydroxide and become ammonia again. Ammonium can give away that hydrogen and become ammonia again. So whatever was the base in the forward direction, that is going to be the acid in the backwards direction. Let's look at a couple other pairs. Any two substances related to each other by the transfer of a proton are what we call a conjugate acid-base pair. So here is water again, and its conjugate acid-base pair, or one of them. Let me show you the other one. So this is what happens when water loses a hydrogen to form hydroxide. But what if water gains a hydrogen to form hydronium? Right? So in this case, water, let's see, it's the acceptor. So this is the base. Water is the base. It accepts a hydrogen, and now hydronium is the acid. So hydronium can donate a hydrogen and turn back into water, H2O, which is a base. But water can also be an acid, and it can lose a hydrogen. So water's right in the middle. Remember, it's amphoteric. There are other amphoteric substances. Let me show you another one. This guy right here, HSO4 minus, is amphoteric. I'll show you why in a second. Let's just examine this equation, and then we'll look at why it's amphoteric. So what we're looking at here is a typical acid-base reaction, and your job here would be to identify who the acid and base are, and then who the conjugate acid and conjugate base are. So what you see here is H2SO4 and water, and then we see what they formed, and we have to decide, okay, who lost a hydrogen, who gained a hydrogen. So you would look at H2SO4, and you'd look over here and try to find which one of these has all the leftovers of H2SO4. Obviously the one with SO4 in it. So, and then it only has an HSO4. So it's missing a hydrogen. So this guy lost a hydrogen when it turned into this guy. So that makes you an acid. When you're a donor and you lose a hydrogen, you're an acid. Automatically that makes water the base. And so water has to gain a hydrogen. Let's see if that happened. H2O became H3O. Perfect. So if water was the base, then H3O plus is now the conjugate acid. If I was to write this equation backwards, let's just see what would happen. So I got H3O plus and HSO4 minus, and they form H2SO4 and H2O. I just want you to see how we would name these. So we would look initially to see what do we start with and what do we end up with. Who's losing a hydrogen, who's gaining one. It looks like HSO4 is going to gain a hydrogen to become H2SO4. So this is the base. And since this is the base, this guy's automatically the conjugate acid. And then we come over here to H3O plus, and we know now, that if this was the base, then this has to be the acid. And so if H3O plus is the acid, then H2O is the conjugate base. And then we can compare and make sure that we haven't done something wrong. Is water a base in both scenarios? Yes. Is there a difference between a base and a conjugate base? No. A base is a base. We're just calling it the conjugate base when they're on the product side. So that's why H3O plus here is the conjugate acid of water, but over here H3O is just the acid, and water is the conjugate base. So whatever's on the reactant side is just acid or base. Whatever's on the product side we call the conjugate. But there really is no difference between H3O plus being an acid or a conjugate acid. It's an acid or it's not an acid. It's an acid or it's a base. Okay, hopefully that was clear. Let me show you how HSO4 is also amphoteric. So let's take HSO4 minus and react that with water. So we saw here that HSO4, well, any molecule that can be an acid or a base, right, is amphoteric. And so those are going to basically describe all of our conjugate acid-base pairs, really. What am I trying to show you here? I guess what I was really looking to show you guys is the other form of HSO4. So HSO4, when it acts as a base, can become H2SO4. H2SO4, by the way, is only an acid. H2SO4 is not a base, and it can never be a base. So that's not amphoteric. Water is a base and an acid sometimes. We saw that. I showed it to you a couple of minutes ago. So that's why it's amphoteric. H3O plus cannot be a base. That thing's only an acid. So that's not amphoteric, right? Water is amphoteric because it's right in the middle between H3O plus and OH minus. So because it's in the middle, it can go both ways. That makes it amphoteric. H3O plus is on the end, so it's not amphoteric. OH minus is on the end. It's not amphoteric. There's nothing else. We don't have. This doesn't happen in nature. I mean, this could happen, but it doesn't happen in water or anything like that. So we can't make hydroxide be an acid or a base. It's only a base. So some things are not amphoteric. This guy is amphoteric right here, HSO4, because it can be a base and turn back into H2SO4, but it could also be an acid and lose a hydrogen and just form SO4 2 minus. So when it's acting like a base or when it's acting like an acid, and it can go both ways. So amphoteric species can go both ways. Just wanted to show you that one other example. Okay, let's talk about some neutralization reactions. Actually, let's do an example. Let's do one more example. So let's pull up. How about I give you C2H5N and H2O. I'll tell you what they form. C2H5 NH plus and OH minus. Your job is to write which is the acid, which is the base, which is the conjugate acid, which is the conjugate base. All right, pause it, give it a shot. I'm going to tell you in 1 second. All right, so this is the acid. How do I know? Because when it turns into hydroxide, this is the conjugate base. Remember, hydroxide can only be a base. Water can be both, but hydroxide can't be both. That makes this the base and this the conjugate acid. Now let's just make sure that that transfer of protons went the right way. The acid donates the hydrogen. Did this base over here gain a hydrogen? Seems like it. So that works. All right. What about one final thing here? Let me give you a couple of pairs, and you tell me if they're acid-base pairs. So HI and I minus, and let's do CO3 2 minus and HCl. Okay, so are these acid-base conjugates? The way you tell is you just look to see if they are different by one hydrogen. One hydrogen. Here's another one. PO4 3 minus, H, PO4 2 minus. So can I add or take away a hydrogen and make the other one? Well, yeah, for this one I can take away a hydrogen and make this one. So that means they're a conjugate acid-base pair. What about here? Can I add or remove one hydrogen and make the other? Yeah, adding one hydrogen to PO43 minus makes this. So they are acid conjugate base pair. Does this turn into this with any amount of hydrogens? No. Does this turn into this with the transfer of one hydrogen? No. Both of these can turn into water with the transfer of one hydrogen, but to turn into each other would require two hydrogens to be transferred, right? This one has 3, this one has 1. You'd have to lose 2 or gain 2. So that's just how you can spot some acid-base conjugates. Let's talk about neutralization reactions here so we can do some. When an acid and base are mixed, hydrogen from the acid combines with hydroxide from the base to form water. You remember this from chapter 7. Now, acid-base reactions generally form water and a salt, the ionic compound that usually remains dissolved in the solution. If it precipitates, then we would have a combination acid-base and precipitation reaction. You can see here an example of those types of reactions. An acid and a base forming water. Now in this case, this formed a gas. This formed H2CO3 as an intermediate, and then this broke down into water and CO2. Hopefully you remember that from chapter 7. But in general, acids and bases will form water and a dissolved salt. And so if we looked at all the total ionic, remember, H plus, Cl minus, K plus, OH minus, we only break apart things that are aqueous. And then we cross out everything that's the same on both sides. You see water is left standing, OH, and H. So we would just have a net ionic equation for most acid and base reactions as H plus OH equals H2O. Now, we did talk about that metals can dissolve. Acids will dissolve metals, and the reaction between acid and a metal usually produces hydrogen gas, so I've given you a few examples here, and some dissolved salts. Some metals do not readily react with acids. So if the bars that imprison James Bond, let's say in that earlier example, were made of gold, then a pen filled with hydrochloric acid wouldn't have worked. And remember this, there was a way to determine if a particular metal will dissolve in acid based on that experiment that we looked at, Chemical Reactions 2, where you saw an activation series, which, by the way, many of you were
putting your activation series backwards, you thought silver was the most reactive, when in fact it was the least reactive. So go back and check that. But in chapter 16, we can look into the reactivity series a little bit more. Now, acids do react with metal oxides to produce water and a dissolved salt. And so here's an example of that. Hydrochloric acid reacts with potassium oxide to form water and potassium chloride. Metal oxides, of course, being not strictly, bases, like acid-base reactions, but this is just showing some reactions of acids. And then hydrobromic acid, of course, reacts with magnesium oxide to form water and magnesium bromide. There are some neutralization reactions with bases that are worth talking about. Most important one is, of course, where bases neutralize acids. But one other kind of base reaction that we cover is the reaction of sodium hydroxide with aluminum and water. And so I've got that reaction down here. So these are just important reactions of acids and bases. Aluminum is one of the few metals that dissolves in a base. If your household plumbing, for example, was made of aluminum, it wouldn't be safe to drop any kind of sodium hydroxide, which is the main ingredient in drain opening products, to unclog your drain, right? Because it would eat right through your pipe. So fortunately, the use of aluminum in piping for that kind of stuff is forbidden in most building codes. Now, like I said before, the main reason, the main reaction for bases is to neutralize acids, and we do take advantage of that quite often in the lab in a form called titration. So it's a way to quantify the amount of acid or base in a solution. So solution stoichiometry can be applied to a common laboratory procedure called titration. Titration, in a titration, there's a substance in a solution of known concentration that's reacted with another substance in a solution of unknown concentration. So I guess I could show it like this. I could be like, this is known molarity, unknown molarity. So I don't know what the molarity of my HCl is. I've got some, but I don't know how concentrated it is. I can use a solution of sodium hydroxide that I do know the concentration of to find the concentration of the unknown stuff. And I don't even have to use it all to find out. I can take 10 milliliters of it or whatever, and I can react just enough sodium hydroxide with those 10 milliliters to find out all the info I need to know about the concentration of the entire thing. And so we're going to look at that right now. The equation we're going to be looking at is the acid-base reaction between hydrochloric acid and sodium hydroxide. Okay. Did I go through having you guys write any kind of neutralization reactions? I didn't. Let's write one or two equations before we move on here, just real quick. Just as an example, I know that chapter 6 or chapter 7 had a lot of this, but let's just do one anyways. Let's write a neutralization reaction, just to give you an example. So let's take, let's say, nitric acid, and let's write a balanced neutralization reaction with strontium hydroxide. Just to give you guys an idea of what you would do. So we're going to double displace, right? Or we could remember what's supposed to happen in neutralization reactions. We're going to form water and a salt. So where does the water come from? Hopefully you can see it. The H in the acid and the OH in the base. So these are going to react to form HOH, or water, and a salt. The salt is going to be the leftovers of our acid and base. So it's going to be this NO3 and this SR. Now the SR I know is SR2+, because it has two hydroxides on it, right? If we were looking at the charges, these are 2+ for the SR and minus for the hydroxide, but there's two of them. Over here we have a +1 for the hydrogen and a -1 for the NO3. So when we pair these up, we should be pairing them up properly.
SR is going to end up getting 2 of these NO3s. Now, we need to have 2 NO3s to give SR 2 NO3s, so we need to put a 2 here. And then if there are 2 H's on our acids and 2 hydroxides in our base, that's going to get 2 waters at the end. So that's what you would do to balance it. So this is balanced now. 2 HNO3 and an SROH2 gives us 2 waters, and SrNO3 2. Where this is probably soluble. We would have to look in the solubility table. Actually, it's got NO3 in it. Nitrates are always soluble. Okay. Other examples that you could do, you could write balanced equations for metals reacting with an acid like HBr. You could show metals reacting, metal oxides reacting with HCl or HI, something like that. Okay. We're not going to go in. I'll show you one example. Sorry. I will. I'll show you one. Let's do magnesium plus HBr. So magnesium, we know metals that dissolve in acids like this are going to form hydrogen gas. So H2. So right off the bat, 2 H's. We only have 1 H over here. So we're probably going to need a 2. And we know that Br forms a minus charge, and we know that magnesium forms a 2 plus charge because it's in column 2. So the formula will be like that. And again, these are usually soluble. This is probably a solid to start with. So that's your balanced equation for writing or for dissolving a metal in acid. And then let's just do one for a metal oxide. So let's take K2O and react that with HCl. So again, we're still going to form water and a salt. The salt here is going to be KCl. We have 2 Ks and only 1 Cl, so we're probably going to need a 2 here. That helps with the 2 H's that we would know we need for the water, and there's already 1 O in there, so everything looks pretty balanced. Metal oxides are solids. Okay, so that's what typical balancing looks like, or equation writing for these acid and base reactions. Okay, let's do some titration. So in a titration, the HCl solution is represented by this molecular diagram. Inside this flask, you see the H pluses floating around. You don't see the Cl minuses floating around, but we don't need to worry about those. They're not involved in the reaction, and so they've been omitted, so we can just see the H pluses. Now, the hydroxides are also in solution, and the NAs and waters are not shown there as well. The hydroxides are going to be, right, because this is known, known and unknown. Oh, I could have made that the unknown. Whatever. So the known solution, we're going to feed into the unknown solution in our flask. Okay, so that's down here. Now, at the beginning of the titration, I need to mention one other thing. We want to be able to tell when we've added exactly the right number of hydroxides that cancels out the number of hydrogen ions in our sample. Essentially, this is going to tell us when we're at the equivalence point. And there's a few ways to do that. One is to monitor the pH, because if the pH goes right to 7, then we know that we've hit the neutral point. That only works when you've got certain kinds of acids. We could also use an indicator, and in this case, we're going to do that. We're going to add a pink indicator. This pink color will show up once we've basically gone past the equivalence point. So as light a pink as we can get will be as close to the true equivalence as possible. If you end up going too dark, too pink, then really we're getting a little bit inaccurate, and we've added too many of our hydroxides. But this is how it works. You start to add hydroxides, and these hydroxides will fall in and start to pair up with hydrogen ions to make water. And when you've basically added just enough so that every single hydrogen ion has paired up, and then you add one more, the solution will start to turn pink. So you want to try to get just that one extra one in there, and that's almost impossible, but you want to do the best you can. Light pink color. And then we do a calculation. So once we've done that, once we've added and we've found our equivalence point by using the indicator, I think I have a real picture here to show you. Yeah, here we go. So in a typical situation, you'd also like to be kind of swirling your flask to help everything mix, but you also are dropping these droplets in very, very slowly. And the good thing about a burette is that it has very small graduations on it, so we can easily tell how many milliliters or fractions of a millimeter we've been adding. And you can see here, once the pink color shows up, often you just swirl your flask a little bit and the pink color goes away. And it starts to pile up right here. And then you swirl it and it just goes away because there's lots of hydrogen ions out here on the sides that haven't been reacted with yet. But eventually the color will last and persist and not disappear. And that's when you know that you've made it to the end. Now, there is a calculation that you would do, and it involves using m equals moles over volume twice. Because remember, molarity is calculated by moles over volume, and for each of these things, we can identify them. For example, moles of HCl is inside your flask, right? Or moles of hydrogen ion, whereas moles of hydroxide was inside the burette. So these moles are different, so two different equations. The volume that we used of our acid is the volume of this little flask. But the volume that we used of the sodium hydroxide is how much came out of this burette. So again, two different equations, two different molarities. And so this is molarity of the acid, this is molarity of the sodium hydroxide. What relates them together is that if we use stoichiometry, we can say that the moles at equivalence are the same. And that will actually tell us. So basically what we're saying is we are looking at this flask, right? And this is what it looks like. It's just clear. And we don't know how many hydrogen ions are in there. It turns out there's 5, right? There's 5 hydrogen ions, but we can't see them. So what we do is we slowly add sodium hydroxide until we get a pink color. And then we go back and look and see how many we added. And it says, oh, you added 5. You added 5 until it turned pink. Because we do know. We do know exactly how much is coming out of this burette, and we know what its concentration is. So when we stop at the right time, we can go back and check how much we added. And we'll know, oh, we added 5 hydroxides because there was 5 acid molecules in there. So that's what a titration is used for. So let's do an example. Let's do an example. So let's say that we have a titration of a 10 milliliter HCl solution of unknown concentration. And into it, we were using our sodium hydroxide, and it took 12.54 milliliters of our sodium hydroxide. That was 0.100 molar in order to reach a nice light pink color. So how do we use that information now to find the concentration of HCl? Well, first we need an equation. HCl plus NaOH. We need to balance it. H2O and NaCl. Well, that was easy. And it doesn't require much balancing, right? 1 mole of HCl will cancel out 1 mole of sodium hydroxide. So it's a 1-to-1 ratio. So let's start. Let's figure out then how many moles of sodium hydroxide we added, because that's how many moles are inside this flask of HCl. So in order to get moles, we take our big M equals moles over liters equation, and we rearrange it. So molarity times liters will equal moles. So I've got molarity at 0.100, and liters, I've got 12.54 milliliters. I'm going to put that into liters. It's 0.01254 liters. I just moved the decimal place over 3. So I got my calculator, figured this out. 0.1 times 0.01254 is 1.254 times 10 to the minus 3 moles. That's how many moles of sodium hydroxide I added. Now, according to my equation, that's all the amount of HCl that was in there. Because remember, my equation tells me how many moles of one thing cancels out moles of the other thing, and here they're both 1 to 1. So if I know how many moles of NaOH I have, well then, according to this equation, I also know that I have 1.254 10 to the minus 3 moles of HCl. Now, the question is, what's my molarity of HCl? Well, that depends on volume. And the volume of HCl was 10 mils. So that's 0.010 liters of HCl. So now I'm at my answer. The molarity is just my moles divided by my 0.01 liters, or 0.1254 molar. So we can see how we can kind of set this up and use how we can use the balanced equation and the molarity equation of just moles over liters to actually solve for the concentration of one of these unknowns. Let's do one more. I'm going to pick a slightly harder one. So let's say that we've got a 25 milliliter sample of H2SO4. "25 milliliters of it. We don't know the concentration. We are going to react that H2SO4 with some potassium hydroxide, KOH. And this potassium hydroxide has the concentration of 0.1322 molar. And it took 41.22 milliliters in order to reach the equivalence point, or that light pink color. So you can compare the volumes here, right? 25 mils of H2SO4, but it took nearly 41 mils of KOH to neutralize it. So the question is, what's the concentration of the H2SO4? We need an equation. We know that we're going to get a water, and we know that we're going to get a salt. K and SO4 make K2SO4. K2 means that we need 2 Ks, and over here we only have 1, so I'm going to put a 2 in front. Scratch that. I'm going to use blue so it stands out. 2 in front. And we already have an H2SO4, so that H2 means that I have an H2 over here with my water. My H2 and my 2 OHs now indicate that I have 2 waters. Okay, but that's not important. We don't really care how much water there is. We just want to know the relationship between the acid and the base. Okay, same thing. Let's figure out how many moles of base we added. So molarity times liters is moles. We've got 0.1322 molar times 0.04122 liters. 0.1322 times 0.04122. So this is 5.4, I'm going to call it 45 times 10 to the minus 3 moles of KOH. So that's how much base we added. Now we're going to use that to find out how much acid there was in the flask or in the container. So we say 5.45 times 10 to the minus 3 moles of KOH. Stoichiometry time. 2 moles of KOH reacts with 1 mole of H2SO4. So how many moles of H2SO4 were actually in there? It's going to be the 5.45 10 to the minus 3 divided by 2. So 2.7 2 times 10 to the minus 3 moles of H2SO4. Right? This equation says that it takes twice as much KOH as the H2SO4. So even though we found out how many moles of the KOH we added, that was not the same as the moles of acid that were there. It was actually twice as many moles as the acid that were there. So we had to divide by 2. So now the molarity of the acid is going to be the moles, 2.72 10 to the minus 3, divided by the volume. And the volume here was 25 mils, so 0.025 liters. We get that the molarity is 0.109. 1090, if we're doing 4 sig figs. 3 sig figs, 109. So that's the titration problem. We knew all the information about one of these. We just needed to find the information about the other. Both of these get an M1 a moles over liters equation. But here on the KOH, we know molarity and liters, and we use it to find moles. We use the balanced equation to relate moles of one to moles of the other, and then we use what we know about moles and volume to find molarity. So it's kind of like a three-part thing that requires having a balanced equation and a properly written equation. All right, practice those. Gotta try them. All right, now strong acids and weak acids, and strong bases and weak bases are things. So let's talk about these first. Strong acid, hydrochloric acid (HCl) is a strong acid, and hydrofluoric acid is a weak acid, though they may appear similar. But there's an important difference between the two. One's strong and one's weak. And so what's the significance? Well, a strong acid completely dissolves in water and has no leftover intact HCl molecules. So a strong acid is one that completely breaks apart and has no more HCl, and we show that with a single arrow going forward. Now, conductivity of pure water, we know, has to do with the amount of ions that are in it, and so strong acids are really good strong electrolytes. And so, this is that experiment. I don't think I showed you the experiment with the light bulb, but we did talk about how ions are the things that move. And so here, this is water with no ions. This is water with a strong electrolyte in it. Now, I'm going to show you a table of some strong acids. There is a table also in your on your formula sheet that you could look at. So the strong acids, there's only 6 of them. Out of all the acids, it's easier to learn the strong acids than it is to learn which ones are weak, because there's only 6. So you could memorize this. 5 of the acids are monoprotic, meaning that they only have one hydrogen that comes off. Sulfuric acid is a diprotic acid, meaning that it has 2 hydrogens that it can lose. So these are strong acids. Let's talk about weak acids. Weak acids like HF are represented with a backwards arrow in their equation, because this F minus isn't a really good conjugate base. It's a really actually, I should say it this way, it's a good conjugate base compared to an HCl. The Cl minus is a very, very terrible conjugate base. It doesn't act like a base at all. It doesn't want to be a base. It wants to stay negative. Of course, fluorine is different. And so because fluorine is uncomfortable, it wants to go back and get its hydrogen back and become HF again. We don't see a lot as much of just free-floating hydrogen ions. And so you can see that here. For all the HF in this solution, many of them are still HFs, and only a few of them have ionized. And that means that this is not as acidic as HCl of the same concentration. And so these weak acids don't conduct as much. And so we would see a less bright light, a dimmer light. They do conduct, but they'd be less bright. Some common weak acids. Let's see, most of the weak acids are organic, some are inorganic. Mostly carboxylic acids are weak acids. 2 of the acids shown in this are diprotic, one's triprotic, meaning it can have 3 hydrogens. Sulfurous acid and carbonic acid are both weak in their protons. Phosphoric acid's weak in all 3 of them. Sulfuric acid, the one that was listed on the strong acids, the diprotic one, it's a strong acid in its first hydrogen, but it's a weak acid in its second hydrogen. So they're not always the same. And to that effect, let's see. I'm going to come here real quick so I can write some stuff down and give you a question. So one of the things that we would do is we would want to determine what's the concentration of acid. And so if I went, here's 1.5 molar HCl, what's the concentration of that? Because this is a strong acid, the concentration of hydronium, or H3O plus, would be 1.5, right? It'd be exactly what the molarity of the molecule is, because it would completely break apart. Now, if I asked you the same question about 3 molar acetic acid, or I think this is acetic acid, HC2H3O2, and I said, what is the concentration of this going to be? Well, it's impossible to know without a pH meter or doing some kind of math, temperature, and all that stuff. But what we could say for sure is that it's going to be, whatever it is, less than 3 molar. Because only strong acids completely break apart. And since this is a weak acid, meaning it's not on our list of the 6 strong acids, we know that it at some point is all paired up as a molecule and not completely ionized. So at the very least, it's going to be less than what we would have expected from a strong acid. And that's what we're getting at here with these types of questions. There's no other way to determine this. It's a weak acid. It completely, if it doesn't completely ionize, then all we could say is the concentration would be less than whatever the concentration of the solution is. If it's a strong acid, we say it is equal to that concentration. So just to give you another example, here's another strong acid, nitric acid, HNO3. So if I had a 2.3 molar HNO3 solution and I wanted to know how much H plus there's actually in there, it would be equal to 2.3 molar. That's what we're talking about. Okay, a strong base. Strong bases are ones that completely dissociate in solution. These are the lists of strong bases. Unlike diprotic acids, which have 2 steps when they lose their hydrogens, bases that have multiple hydroxides, they all just come off in one step. Just dissolves like a normal thing. And so you can see here sodium hydroxide dissolving. It forms the hydroxide part. That's the base part. And yeah. So I've got 2 equations here. The first equation is just, or actually this equation that I'm showing you here is the equation for a weak base. So a weak base is one that doesn't produce hydroxide on its own, but as a reaction with water. So we saw that ammonia was a weak base. Ammonia was not an Arrhenius base. It was a Bronsted-Lowry base. And also ammonia reacts as a proton acceptor to pull a hydrogen off of water. And that's what we're showing here in this equation. So most weak bases will do that. They'll pull a hydrogen off of water to form some sort of conjugate acid, right? But to produce hydroxide. And so that's why these things are bases. Now, weak bases, again, only pull off a few hydrogens off of water molecules. And so we're not going to see as much hydroxide compared to, a strong base. Got some weak bases here. So ammonia is a weak base. Pyridine, methylamine, ethylamine, bicarbonate. These are all weak bases. Many weak bases. Organic amines are weak bases. Okay, and you can just see all of these bases, right? They all become conjugate acids. All right, and the same thing goes when we're determining concentration of bases in solution. If I tell you that your base is strong, if I say you've got 2.25 molar of KOH, and I want to know how much hydroxide there is, it's a strong base, so this is going to be equal to 2.25 molar. If I give you something like calcium hydroxide, and I say this is 2.25 molar calcium hydroxide, what is the concentration of hydroxide? Hopefully you're going to realize that this has twice as much hydroxide in it as the molecule itself, right? It's like saying every car has 4 tires. So if there's 10 cars in a lot, there's actually 40 tires in the lot, right? This thing has 2 hydroxides per molecule. So even though we have 2.25 moles of this molecule per liter, we actually have 4.5 molar hydroxide total. So be careful when you're, on the homework when you're asked about concentrations of hydroxide. The other thing would be if it's a weak base, all we would be able to say is that it's somewhat less than, 2.25. If it was a weak base. I don't believe there are any weak bases that are that give you multiple hydroxides. So you're either going to be dealing with a multiple hydroxide type strong base or a weak base that only has 1 hydroxide. Okay, moving on. What's going on here with my pen? Sorry about that. Okay, water as amphoteric. This is just showing you that again. Now, we're going to use this to kind of spring off on a definition of acid and base that we can use our pHs for. So again, acid and base means amphoteric. You can be either. Pure water can do this with itself even. It doesn't even have to be an acid reacting with water or water reacting with an acid. Or water reacting with a base. Water can literally react with itself. We can have H2O and H2O. One of these will be an acid, one will be the base, one will become H3O plus, one will become hydroxide. And we get what was called the auto-ionization of water. Okay? And so this happens. Now, because this happens only to a small extent, we always, and of course always results in an equal amount of of H3O and OH minus. This doesn't change the pH of water, right? Pure water does this, but these cancel each other out. The pH is always neutral, but there is some amount of H3O plus and hydroxide floating around, and we can quantify these. And so for pure water at 25 degrees Celsius, so at 25 degrees Celsius, H3O is equal to hydroxide, and these are equal to 1.07, or sorry, 1.0 1.0 times 10 to the minus 7 molar. So both of these are equal to each other, and they're all equal to this number. So this is just a definition. At 25 degrees Celsius, because water auto-ionizes with itself, we have this amount of each of these in water. And so if we wanted to know the total ion amount of these guys, we multiply them together. We come up with something called H3O plus times hydroxide equals what we call Kw. And Kw is just this number for both of these. So it's 1.0 times 10 to the minus 14. This is where pH comes from. pH being neutral, right? pH is 7. The pH scale going from 0 to 14 or 1 to 14. It's from these numbers here. In a neutral solution, the H3O is equal to the OH minus. Okay? The concentration of one is equal to the other. And we just defined that. We just said that that was true. Because in pure water, they ionize each other. They form at the same time. There's always one hydroxide for every hydronium. So these are going to cancel each other out instantly. And at 25 degrees, there's this much, 1 times 10 to the minus 7 of each of them. So together, there's 1 times 10 to the minus 14. That's what we call the Kw, and it'll let us find out how much of one ion we have when we know about the other. So let me show you how that would work. So first, let's clear this. Let's calculate how much hydroxide there would be when there's a hydronium concentration equal to 7.5 times 10 to the minus 5 molar. Okay? So here's a couple of things. First, let me give you two hydronium concentrations. Okay. Now, there's two ways to tell if your solution is acidic or basic, okay? Or neutral. That's to look at the amount of hydroxide and hydronium and see which one you have more of. Whichever one you have more of, if you have more hydroxide, then that's going to be a basic solution. If you have more hydronium, then that's an acidic solution. We can also just look at how much hydronium there is. Remember, a neutral solution has 1 times 10 to the minus 7 hydronium and hydroxide. Here, we can already tell by this 1 10 to the minus 5 that that's more hydronium than we would want at neutral, right? 10 to the minus 7 is a smaller number than 10 to the minus 5. So this seems to have a lot more, this one on the top here has a lot more hydronium than we would expect at a neutral solution. So that might imply that it's acidic. On the bottom one here, 10 to the minus 9 is a smaller number than 10 to the minus 7. So if we, at a neutral solution of pH 7, normally have 10 to the minus 7 hydronium, and here we have 10 to the minus 9, which is much less, that might be a basic solution. But again, we can compare the hydronium to the hydroxide to see. So what we do is we say H plus times OH minus equals 1 10 to the minus 14, or kW. So if we know one of these, we know the other, because here we know hydronium. So we can say hydroxide is just 1 10 to the minus 14 divided by whatever concentration of hydronium is. So we can literally just take 1.0 times 10 to the minus 14 and divide it by this number, 7.5 times 10 to the minus 5, and that tells me that my hydroxide is 1.33 times 10 to the minus 10. And so now we can quickly compare. Which one is greater? Looks like I have a lot more of the hydronium than the hydroxide, so this is acidic. What about in the bottom one? Same thing. 1.0 times 10 to the minus 14. We're going to divide by the hydronium concentration, 1.5 times 10 to the minus 9. This says that I actually have 6.7 times 10 to the minus 6 molar hydroxide. So which one's bigger now? Well, this is a bigger number. So whichever one's larger, right? Larger amount of hydroxide, so this is basic. So that's how we can tell if a solution is acidic or basic, by comparing hydronium to hydroxide. But we can also be given hydroxide or hydronium, and we can use it to find what the other concentration is. Okay? The pH scales are basically just summaries of this. So let's take a look at it. So there's an interdependence of hydroxide and hydronium in acid or base solutions. Okay, we can have lots of hydronium, we can have lots of hydroxide. In water, that's not the case. In water, they form at the same time, but water is always neutral. Acidic solutions and basic solutions are not neutral by definition, so there is going to be more of one or the other. And so the pH scale and the pOH scale are just ways of expressing acidity and basicity. This is the I've got the two scales here. This is the pH scale shown. I'm not showing the pOH scale, but the pOH scale is based on this bottom line, and this pH scale is based on the top one. So if we know the concentration of hydronium, then the scale relates to those concentrations. So having 10 to the minus 0 is going to be at the low end of our scale. 10 to the minus 1, 10 to the minus 2, these numbers are getting smaller. 10 to the minus 14 is a tiny amount of hydronium. So you would expect a tiny amount of this acid molecule to be present in a very basic solution. On the other hand, hydroxide, which is the base molecule, you would expect to be in high concentrations in base. So the pOH scale is actually backwards. When we say something is acidic and has a low pH, we would say something is basic according to the pOH scale and say that it has a high pOH. So again, the numbers are going to be a little bit different. What I mean is acidic would be low pH, but it would be high pOH. So we don't usually mix and match these different scales, but I'll show you how we can relate them in a minute. Okay, just to give you an idea here, too, I'm gonna show you how these numbers up top get converted into these pH numbers in a second. The pH scale is actually an increase by a factor of 10. So every time we go up by 1 pH unit, or decrease by 1 pH unit rather, we increase the concentration of hydronium by a factor of 10. So if this was the amount of hydronium at pH 4, then this is at pH 3, then this is at pH 2. So we're getting more and more and more logarithmic. Okay, we can calculate the pH from the hydronium concentration with a simple equation. The pH is simply going to be the negative log of whatever concentration we have. So give you an example. Your hydronium concentration is 1.8 times 10 to the minus 4, or it's 7.2 times 10 to the minus 9. What is the pH? And so you take your calculator, you plug in the negative log, or I like to plug in this number first and then go negative log and then hit my answer button. But you just go in there and you plug in a negative log and you get, for the first one, 3.74. If you do the second one, you should get 8.14. And I encourage you to take a look at the numbers. Remember, 10 to the minus 7 is neutral. 10 to the minus 4 is a bigger number than 10 to the minus 7. So it's going to be more acidic. So we would expect this to be a lower pH. 10 to the minus 9 is a smaller number than 10 to the minus 7. So it's going to be less acidic than even neutral. So it makes sense that the pH would be 8 into the basic range. Okay, that's calculating pH from hydroxide concentration. Now, you can also calculate the hydroxide concentration from the pH. Let's try that. Now, for this one, it's the equation is actually here. Now, well, I'm sorry, to show you how to get to the equation, which one is it? Yeah, don't use the inverse log function. Use the 10 to the, well, it doesn't matter which one you use. I use this one. So I'm sorry. Let me show you what I'm trying to tell you. Due to this equation, right, if pH is equal to the negative log of the hydronium concentration, then we can actually rearrange for hydronium on its own down here in this equation. So whether you use the inverse log or you use the 10 to the minus method. So let me kind of show you what that is. So you would go 10 raised to the minus pH, and that'll give you back your hydroxide concentration. Or you do inverse log of the negative pH. Inverse log negative pH. This will give you back your hydronium. Both of those will work. So if I give you a pH of, let's say, 4.80, and I ask you to calculate what the concentration should be, then you would plug in, oh wait, 4.80 is already shown, my bad. Let me give you a different number just for fun. 4.80 is this example right here. It's already showing you 4.80, and you can see both methods give you the exact same answer. So let me pick, let me just show you how this works. So let's pick a pH of 7. So a pH of 7, So we would go 10 to the negative 7, and I get that concentration is equal to 1 times 10 to the minus 7. So exactly what we would expect for the hydronium concentration at a neutral pH. It's exactly what we thought it would be. So let's go slightly less than that. What about 6.3 pH? So it should be a slightly larger concentration than this. 10 to the negative 6.3 is 5.01 times 10 to the minus 7. So is 5 10 to the minus 7 bigger than 1 10 to the minus 7? Yes. Is it as big as 1 10 to the minus 6? No, but it is still there. And if you notice, all of these whole numbers, 1 10 to the minus 6, this is pH of 6. 1 10 to the minus 5, that's pH of 5. So there's actually a really neat relationship between the whole number of pHs and the 10 to the minus number of pHs. So just to show you, pH of 9 has a hydronium concentration of 1 10 to the minus 9. Okay. That's how you find pH from hydronium ion concentration, and also how you find hydronium ion concentration from the pH. Let's talk about buffers real quick. Buffers are solutions that are resistant to change. And actually, I do want to take a step back real quick and give you one more little bit of information here. So there's another couple of relationships that I want you to use. This will help you with your homework. So we know that hydroxide and hydronium are related together through the Kw. So as long as we know that number and one of the other two, we can find the other. There's also that pH plus POH equals 14. So if we know the POH, for example, and we're asked for the pH, we can find it through 14. We know everything about pH, that pH is the negative log of the hydronium ion concentration, and that the 10 to the minus pH will get you your hydronium ion concentration back. But POH follows the same. It's the negative log of the hydroxide concentration. And if you know the POH, you just say 10 to the minus POH, and you get back your hydroxide concentration. So these equations should help you when you're doing your homework. Often there's a problem that'll say something like, what is the hydroxide concentration for a solution that has a pH equal to 3.66, right? You can't just take 10 to the minus pH and get hydroxide. 10 to the minus pH gets you back to your hydronium ion concentration, but then you need a way to relate these two to each other. And you do have a way. You have the Kw. But now, with pH and POH, you could just say, okay, well, pH is 3.66. What's 14 minus 3.66? 10.34. So if the POH is 10.34, you could just undo the POH and get the hydroxide back. So there's a lot of utility to knowing these equations. Okay, buffers are solutions that resist change. They contain a significant amount of both a weak acid and its conjugate base, or a weak base and its conjugate acid. The weak acid that's there neutralizes any added base. The conjugate base will neutralize any added acid. Human blood, for example, is a buffer. In healthy individuals, blood pH is about 7.36 to 7.4. But if your blood pH were to drop below 7 or rise above 7.8, you'd die. And so in these two examples I'm showing you, the acetic acid and the acetic acid sodium acetate buffer system. So this is acetic acid right here, and this is sodium acetate. They are conjugate acid bases. Again, acetic acid, sodium acetate, conjugate acid bases. But they have, in different circumstances, can act as different buffers. So if I were to add acid to my buffer, the acid would react with the base form of my conjugate pair to neutralize that acid and to form a salt and to actually turn some of my base back into my conjugate acid. But you'll notice the HCl, the strong acid, is gone at the end, right? It's gone. If we were to add sodium hydroxide to this buffer system, instead, the sodium hydroxide, the strong base, would react with the acid part of our conjugate. This would neutralize, form water, and it would turn some of the acid back into the conjugate. But in both cases, the conjugate, they are there to protect from acids or bases. Because these, and they, again, it resists the change in pH. And I think I can have a calculation or two to show you that. In fact, just to give you an idea, if I take pure water, which has a pH of 7, and I add 10 milliliters of NaOH to it, the pH of 7 will jump to a pH of around 10. So that 10 milliliters of that strong base jumped it all the way 3 units. Now, on the other hand, if I have a pH of 7 buffered solution, let's say like this acetic acid buffer, and I add 10 mils of NaOH to it, just like in this equation right here, the pH might change from 7 to 7.6 or 7.06. It might go up, but it's going to go up a tiny, tiny bit in comparison. Now, to make buffers better, you use more of them. So the more of a buffer you use, like 100 mils versus 10 mils, is going to be better. And also the concentration. If I make a buffer with 0.1 molar conjugates versus 1 molar or 10 molar, my 10 molar buffer is going to be a lot better than my 0.1 molar buffer in terms of the amount of buffering that it can do. But that's what you use a buffer for. You can see here that buffers provide a way to neutralize an acid that's added or a base that's added. Ethylene glycol in alcohol. Ethylene glycol is an alcohol. And in the first stage of ethylene glycol poisoning, it's actually a kind of drunken state. But once ethylene glycol begins to get metabolized, the second and more deadly stage begins, and this is where it gets metabolized into glycolic acid. Antifreeze is what we're talking about. Ethylene glycol gets turned into glycolic acid in your bloodstream. And glycolic acid quickly and efficiently overwhelms our body's ability to buffer, and our pH drops to low levels. And then basically a poisoned animal, poisoned human starts hyperventilating. The change in the pH changes the hemoglobin in your body to no longer really carry oxygen very well, and so you die. The treatment for that, interestingly, is regular alcohol. So if you get ethylene glycol poisoning, you go to the emergency room and they give you regular alcohol because your body would preferentially metabolize regular alcohol into some relatively harmless metabolites while the ethylene glycol just gets out of your body. All right, so at the end of this chapter, we have talked about acids and bases, the Arrhenius definition, the Bronsted-Lowry definition. We looked at reactions of acid and bases, and we looked at neutralization reactions, writing them, acid and metal reactions, and even acid and metal oxide reactions. We looked at the acid-base titration. We looked at strong and weak acids and bases. We looked at self-ionization of water and how that leads to our pH and pOH scales. And we looked at buffers very, very briefly. So I hope these learning objectives help you kind of narrow down what you need to study. Definitely, let's see, there's a couple, there's a few more. Does it not give you all of them? There's a few more learning objectives. Determine, let's say 7, determine H3O plus and OH minus in solution. Identify strong acids and weak acids, or strong bases and weak bases. Find concentration, find concentration of H3O or OH minus from using the KW. So like if I give you one, find the other. Calculate pH or pOH. pH or pOH from H plus or OH minus, and then backwards. So being able to do this front and back. So pH from H and also H from pH. And same goes for pOH and OH. All right, guys. Good luck. See you in the next video.